Right, I'm going to consider now a different group. I'm going to consider what's called GLN of R, which is n by n real. I put R here, but it could be complex, but real matrices, invertible. So if M is a member of this, I'm just going to call that G for my group, yeah? So if M is a member of G, then M to the minus 1 is a member of G as well, just regular matrix inversion. And we've seen a few times, I think, now that matrix multiplication, at least for non-zero determinant matrices, is a nice little group. I'm going to consider the homomorphism phi, which maps G to H, where H is just the group real numbers under multiplication, where phi of a matrix equals the determinant of that matrix, equals det M. We better check its homomorphism first. So I'm checking that phi of M, phi of n equals phi of mn. And so what that basically means is det M, det n equals det mn, which of course it is by regular matrix multiplication rules. Observe again that this product here is just regular real multiplication, whereas this one in here is the group operation of my group G. So this one here is matrix multiplication, and this one here is just regular regular real number multiplication. So what's the kernel of phi? Well, we know it's a normal subgroup of G, normal subgroup of my set of matrices. Well, what's that? That's just M such that phi of M equals the identity, which in this case is just equal to 1. So the kernel of phi is just matrices with unit determinant. And we know that's a subgroup because matrix multiplication commutes past determinant. Well, because of this. Okay, so the first isomorphism theorem says that G over ker phi is isomorphic to im phi. So that tells me that G slash, what shall I call it? I'll call it U, is isomorphic to the real numbers under multiplication, where U is the set of all matrices, real matrices, with unit determinant. Okay, well that's great. So what do the cosets look like? Remember my picture of the coset of G with the cosets look like this. Well, here the cosets are U x, where this is the kernel of the homomorphism, which is matrices of unit determinant. And that's just a real number. Okay. Okay, and what group structure have we got on that? Well, that's just Ux Uy equals U of xy. So what we've got is matrices with unit determinant times x times other matrices of another set of matrices with unit determinant times y is just a set of matrices with unit determinant times xy. So there it is. That's it. I'm going to stop there.